In the previous section, we considered a non-negative random variable capital T, and we looked at 5 different ways of determining the distribution of T. Those 5 different lifetime representations were the survivor function, the probability density function, the hazard function, the cumulative hazard function, and the mean residual life. In all cases, we were looking at a continuous random variable T rather than a discrete random variable T. That's why you saw a lot of integrals and derivatives occur in the transition from one lifetime distribution representation to another. In this section, we consider discrete distributions. And that is, we still have a random variable T, but this time the support of that random variable is discrete rather than continuous. These discrete failure time distributions are less common than continuous distributions in reliability analysis, but they still occur in practice from time to time. So the first question that's asked is, when do you use a continuous and when do you use a discrete model? The real question here is, can failure happen at any moment in time? If it can, then you use a continuous random variable. Examples of this are an operating system which is running continuously. It can fail at any time t greater than 0. Another example, if a fuse is subject to failure and failure can occur at any time, then that fuse has a continuous lifetime. If a machine in a job shop is used continuously, its breakdown time is easily modeled by a continuous random variable. Likewise, if there is a rivet which is subject to fatigue failure, then that's an example. If the stress on that rivet is on a continuous time basis, then a continuous random variable T is appropriate. On the other hand, if failure can occur only upon demand, then that's a case where a discrete random variable T is appropriate rather than a continuous random variable T. Couple examples, software once again, but this time if the payroll program is run monthly, that's a case in which you would want to use a discrete random variable, month 1, month 2, month 3, etc. Starting a motor when something like this is done on demand, and that might be a motor on a lawnmower, for example. Another one is a switch. The cycle number to failure would be a discrete random variable. If you look at the space shuttle, it had brakes that it would apply after it landed. Those would be done on demand, so that would be a discrete random variable. Every time you use a garage door opener, you have a discrete demand. Any commercial domestic aircraft flight, if you don't consider any failures within the flight, but you only consider whether or not the flight makes it to its destination, that's a discrete random variable. Likewise with the landing gear, it's done on demand, stapler, etc. So there's plenty of examples of continuous and discrete random variables, but this particular section is all about discrete random variables. So here are the transitions. The good news is all of the symbols that we had before. The lifetime is T. The survivor function is S. F is no longer called the probability density function. Its name will change to the probability mass function. H will still be the hazard function, capital H the cumulative hazard, and L will still be the mean residual life function. So the non-negative discrete random variable T may assume the values T1, T2, etc., where they satisfy this inequality. And you can think of those times as the times when demands are made on the system. That is also the support of the random variable capital T. Well, let's go through those functions, the 5 of them, in the same order we did below for the continuous case. The first is the probability mass function. That's now given by f of tj, and that's going to be for j equals 1, 2, etc. Now the interpretation of it is actually a little bit cleaner in this case. Before, when you had a probability density function, you interpreted it in terms of an integral. Now it is the probability of failure at time tj. So cleaner interpretation in the discrete case. The survivor function is a left continuous non-increasing step function, and here is its definition. This part of the definition right here is identical to the continuous case, but this time, instead of working an integral from t to infinity, we have a summation of all of the mass values from t to the right of t. So from t all the way out to infinity, you simply add up the associated probability mass function values. So the probability mass function has non-zero mass at t1, t2, etc., while the survivor function is defined for all non-negative t values. So you can think of in a graph, and we'll draw a graph in a few minutes, this will be a bunch of spikes, whereas this will be a step function. Now the next one is the hazard function. The hazard function will be defined on the support values. The magnitude of the hazard function is still interpreted as the risk at time tj. Since time is discrete, the hazard function is no longer defined as a limit. It's much more straightforward. H of tj will be the probability of failure at tj given that the item is still operating at tj. If you remember, when you have conditional probability, down in the denominator you put the probability of the given event, which is right here, and for the numerator you take the intersection of these two events, and that intersection is right here. Now the good news is that top piece, the numerator, is the probability mass function, and the bottom piece is the survivor function. So just as in the continuous case, the hazard function is the ratio of f of t to s of t, but it is only at the support values. Now there is a dilemma on how to find the cumulative hazard function. If you go back and look at the 5x5 matrix, there are two reasonable ways to go. The first is to define the cumulative hazard function as the opposite of the natural logarithm of the survivor function. The second way to go is to define the hazard function as the sum of little h of tj. This is the same as in the continuous case, except for the integral has been replaced by a summation. Either of those are acceptable. We are going to choose the first here, and so the cumulative hazard function will be the opposite of the natural log of s of t, and that is a left continuous non-decreasing step function. Finally, the last of the 5 is the mean residual life function, and this is exactly the same definition as in the continuous case. And if you work through the mathematics in exactly the same fashion as before, but now instead of an integral you have a summation, you get a very, very similar formula for the mean residual life function. Just instead of an integral here inside the brackets, you have a summation. Couple notes: the mean residual life decreases with a slope of -1 between the mass values. And you may remember in one of the existence conditions for the mean residual life, you can never be more steep than a slope of -1. And the last one, as in the continuous case, if you let L of 0 and calculate it, you will get the expected value of t. Here is an exercise, and it is to draw the 5 representations for this function, which is a probability mass function. F of t is 0.5 for t equals 3, 0.3 for t equals 4, and 0.2 for t equals 7. And not surprisingly, those 3 numbers add to 1 as they have to for a probability mass function. So here is f of t. We're going to draw a picture of this thing. And if you want to think of a story that goes behind this, because this is kind of a strange distribution, let's say I take my cell phone and at time 3 I drop it from about 2 feet off the floor, and there is a 50-50 chance that that takes the cell phone out. Then 1 time unit later, at time 4, I drop it again, but this time I drop it from a little bit higher. I drop it from, let's say, 8 feet, and the probability is 0.3 that it fails then. And finally, I climb up to the top of the Eiffel Tower, and I get there by time 7, and I drop the cell phone from there, and now I have 0.2 probability. So kind of a strange experiment, but if you go in here and put a 3 and a 4 and a 7 for your mass values, and then you draw a 0.5 here, followed by a 0.3 here, and finally a 0.2 here, that is a picture of the probability mass function. Now the next function to draw is the survivor function. So once again we're going to have t here. This will be the survivor function, and survivor functions, of course, are defined between 0 and 1. Put our mass values back in there. There's 3, 4, and 7. And the way this looks is the survivor function is going to start out at 1 until it gets to 3. And when it gets to 3, you're going to have a closed circle, and it's going to drop by 0.5. And then at 0.5, it goes across until it hits 4. And at 4, it drops by another 0.3, and now it's down to 0.2. So this point right here is 0.2. It's not cooperating. Anyhow, there's 0.2. That should be an open circle right there. And then finally it comes to 7, and at 7 it drops down to 0, so we will have an open circle there, and it is at 0 thereafter. So there is the survivor function. It is a downward step function, and the amount of each step downwards is given by the values in the probability mass function. Now the next function here is the hazard function. So I'll label that lowercase h of t, and we can put in our mass values again. They are 3, 4, and 7. In this case, you will have ratios of values, and this time I'm going to put some units in over here. Let's call this 0.5 and call this 1.0. And so in the first case, if you take the ratio of the density, and the density right here is 0.5, and then you find the value of the survivor function at 3, and notice the value of the survivor function is 1, so 0.5 divided by 1 gives you 0.5. Then you take the next value. At t equals 4, the height of the probability mass function is 0.3. If you take 0.3 divided by s of 0.3, and you can see s of 0.3 is 0.5, And 0.3 divided by 0.5 is 0.6. So you're going to get a height which is just slightly higher than that. Finally, when you go to times 7, you have a probability mass function value of 0.2. If you take 0.2 divided by S of 7, which is 0.2, 0.2 divided by 0.2 is 1, and the interpretation here is when I drop the cell phone off of the Eiffel Tower, if it is still operating at time 6.9, it's guaranteed to go out. That's the 1.0 when I drop it from the top of the Eiffel Tower. We have two more functions to do. The first one is the cumulative hazard function. And the cumulative hazard function, if you put in 3, 4, and 7 as your mass values, then what you have is along here, you remember this is the opposite of the logarithm of S of t. Well, S of t in this area right here is 1, so the natural log of 1 is 0, so it is going to be 0 here. And then what's going to happen is it will jump upwards, and the amount that it jumps upwards will be the log, the opposite of the log of 0.5. So at this point it jumps up to the opposite of the log of 0.5. And then at this point, at 4, it takes another jump, and now it is at the opposite of the log of 0.2, and so it will jump up to that, and then finally at 7 it will go down, and you're taking the opposite of the natural log of 0. You can't take the natural log of 0, so in this region out here this function will be undefined. Finally, the last of the functions is the mean residual life function. And L of t, if you go ahead and include 3, 4, and 7, L of 0 is the expected value of the random variable. So in this case, to find that expected value, you can just take 0.5 multiplied by 3 plus 0.3 multiplied by 4 plus 0.2 multiplied by 7, and that works out to 4.1. So the mean residual life is going to start out at 4.1, and then it is going to go downwards until, and by the way, it's going downwards at a slope of -1 until you get to 3, and if it survives that, then its mean residual life goes up. It again goes down at a slope of -1 until it gets to here. And then finally, at this point, it comes up again and goes down until it bumps right into 7, and that's where it ends. That is the mean residual life function.